Okay, guys, good morning. Thank you for coming to this first talk. So the keyword of this talk is anonymous, although you know by now what are black box constructions, so really pay attention to the word anonymous. So thanks to Sanjam for the talk yesterday, we know what black box constructions are and why we look at black box constructions. So the idea is you want to create a task A, and you want to make black box call to some primitive B. And you don't know anything about B, you just know the input-output behavior. Now, what anonymous setting is, in an anonymous setting, you have cryptographic objects which are created by people that you don't know. To give you an example, you can have anonymous signatures, anonymous commitment proof. So anonymous signatures are ring signatures. The idea is, in anonymous signatures, you have public keys, which are computed by people that you don't know, but you should be able to compute a signature that verifies under all these public keys. And you only know the secret of one public key, but somehow you should be able to compute something that satisfies, given in input all those public keys, and the verifier should not be able to tell what was the secret key that you knew. Similarly, anonymous commit and proof, you have many commitments. These commitments are made by other people, but you want to prove that you know the opening of one of them. And this is what happens in Zcash. For example, in Zcash, what you do is a proof of equality. So all the commitments are coins. And when you want to spend your coin, you say, well, take all these coins, which are commitments. I know how to open one of these commitments to this number. So it's really a proof of equality made over many commitments. And again, the point is that these commitments are made by other people over time. And you want to make sure the verifier cannot tell which is the commitment you know the opening of. So the key point here is in an anonymous setting, there are objects that you don't know, but you have to work with them in order to compute your proof or your signature. Now the question, natural question is this unknown setting kind of making things harder? So is it harder to prove things if I don't know the randomness of the commitment used by other people? The answer is no, it's actually easy. Because all I need to know is the circuit of the commitment. And then if I want to prove in zero knowledge that I know one of the opening, it's really easy. My statement is the circuit of the commitment. Let's say I want to prove I know how to open one commitment to 13. 13 is part of the statement. All the commitments are part of the statement. And my witness is the randomness of one commitment. And the relation I'm proving is there exists an I, and I know a randomness such that one of the commitments, if you run the commitment circuit with this randomness, and 13, you get one of them. So if you can use the circuit of the underlying cryptographic primitive that was used to compute these objects, there's no problem in computing a commit and proof, for example. And similarly for ring signatures, or if you know some other information about the commitment, if it's a Peterson commitment or an El-Gamal, then you can play with the structure and do something. Now the question I'm asking here is, what can I do if I'm in the anonymous setting and I cannot use the code of the underlying cryptographic primitive? In particular, I'm asking, what if the only thing I can do is to use a random oracle? In random oracle, you don't even have trapdoor. It's not like a trapdoor permutation oracle. It's just random oracle. You have just random outputs. And why does this question make sense? So what we know in the non-anonymous setting, so when, let's say I have only one commitment and I want to prove things about the commitment, we know how to do black box commit and proof. We also know how to build black box signatures from any one-way function, although they are one time. But if you are in a non-anonymous setting, random oracle is just fine for these primitives. Now the question is, can we basically do the same thing in an anonymous setting? And again, the difficulty in the anonymous setting might be that you are dealing with objects that you did not create, you don't know anything about it, and you cannot even leverage the code of the that was used to compute the commitments.
Alessandra?
Yes?
So here you're allowed to come up both with a commitment scheme and a proof, right?
Yes. Yes, that's crucial. And the only thing is I can come up with a commitment and I can only use random oracle in a black box manner. So let's see, what we show is that you can compute black box commit and proof in this anonymous setting. And the nice The nice consequence of this is that if you look at very simple relations like equality, you can, now that you move in the black box setting, you can, the circuit of equality is very simple. There are XORs, few ANDs, few OR, and few ANDs. So it's a really, very simple circuit. And now I can prove equality of one out of many commitments using, if you don't use any circuit, then the relation that you have to prove is much, much simpler. And because we have this tremendous improvement in MPC in the head techniques, the whole thing actually it's efficient. It's not only, I mean, it has some concrete efficiency motivation here. There is also, we also show that you can build ring signatures. Just like you can build one-time signatures from one-way function, you can build ring signatures from one-way functions. And it's a simple construction. It's almost like a textbook construction. You can teach it in a crypto class. It's really, really simple. And the nice thing is, so any ring signature we know now is always based on some trapdoor crypto primitive. So we knew it black box from trapdoor permutation, or we know many non-black box construction from lattices, or discrete log assumption. So we really don't know any ring signatures which does not have some trapdoor crypto primitive inside flavor. So this was from random oracle as the random oracle obviously does not have any trapdoor. The downside is that all these constructions are one time. What does it mean? You can create many proofs using the same set of commitments or the same set of public keys. However, each person can use their witness or their secret key only once. So there is a linkability kind of flavor. So it's a downside, but can also be it can be a plus, especially if you look at how anonymity primitives are used. For example, in Zcash, you want to make sure that each coin is spent only once. So having this one-time flavor can be actually a good thing in some applications. What we don't see show is possibly one-time. And I'll tell you, it will be clear why later, maybe in black box techniques. Reusability, it's hard to get reusability unless you assume some state. Also, another thing that one should look at is, can you achieve some degree of succinctness with black box techniques? This is something we did not look into.
Alessandra?
Yes.
So I'm not sure I understand the statement. You get ring signatures from one-way functions or ring signatures in the random oracle model?
Random oracle.
Okay.
No one-way function, so I need some property of the random oracle, like programmability, for example.
So there are constructions, I think, from one-way functions and NXDK.
Yeah, non-black box use of the code.
It makes you saying this is a problem because it makes, like, you need to do an NXDK tool with respect to the one-way function, and therefore, if you want to use random oracle, then you have it.
You will not be able to do that. Yes. So in some sense, the way I think of it is that either you have a trapdoor oracle, or you can do one-way function, but then your trapdoor will be the code. So you can use the code to build the ring signatures. So if you want to use the one-way functions in a black box way, we don't know any construction. Any other question? All right, so that's what we wanna see, and you'll see they're both very, very simple constructions. So I think I'll spend most of the time focusing on how do we get there, because once I tell you what's the problem, then it's pretty simple to get around it. Okay, so this is the outline of the talk. So I'll tell you a little bit more about what we know in the MPC in the head, technique, and then the ingredients we need to actually achieve black box commit and prove in the anonymous setting. And if we have time, I will go over the one-time ring signatures. But since it's actually very easy, so if you don't have time, we can just talk to me, and it will take me 5 minutes to explain. So just Puya, just tell me if I don't have time, I'll just stop earlier. Okay, so I want to give a little bit of so the background on black box approach. So as Yuval said the first day, we are starting from Killian, but more and more these days, we are dividing the problem of constructing zero-knowledge proofs in two parts. There's an information theoretic part and a crypto compiler. So in the information theoretic part, we assume that there's a prover and a verifier, and somehow the verifier is constrained. He cannot see the entire proof statement. So the prover can write, for example, PCP in the sky, and the verifier can only look at few positions. Now, of course, in the real world, this is not possible, but assume that we are in a world where this is possible. Then you can just focus on constructing this proof in this model. And this is what the PCP-like approach by Kilian, this is how this was introduced by Kilian in some sense, this PCP-like approach. So you focus on the PCP, and you assume that the verifier has only Oracle access to the proof. And there are many works on this approach, which I'm not citing here. What I'm more interested in, because I'm using in my, we're using in our paper, is the MPC in the head approach. So the idea is, instead of the PCP, you actually have the prover running an MPC in the head for the relation that the prover needs to prove. And while it started to be kind of more like a theoretical result, over time, it was observed, for example, by Z.K. Boo, the paper by Claudio et al., that you can take this kind of theoretical construction, and if you use the right MPC protocol, then you can achieve very efficient, concretely efficient proofs. For example, Claudio observes that you can think, instead of using some general GMW or BGW, you can craft your own MPC. You can look at 2-3 decompositions, and which are perfect for the purpose of MPC in the head, and then this will lead to more efficient zero-knowledge proofs. And recently, for example, Katz, Kolesnikov, and Wang observed you can actually use an MPC with pre-processing, and this will make your proof even more efficient. So the point of this slide is to say that even though you start from this information theoretic setting, usually for some theoretical purposes, then this kind of, it can lead to actually concrete improvements. Anyway, so there's the information theoretic part, and then you have to enforce the access of the verifier in some way, because we don't have this ideal world in practice. So what you do, you actually run a crypto compiler and typically use either commitment or hash functions in a black box way to enforce that the access of the verifier is restricted, and to enforce that the prover cannot cheat. Okay? So this is how we get black box zero knowledge. And one note, though, is that any zero knowledge protocol is black box, but it uses the circuit you want to prove, the relation, in a no black box manner. So if I do MPC in the head, the input of my MPC in the head is the relation, and the relation is seen as a circuit, of course. Now, what if I have a black box zero knowledge proof and I want to do commit and prove? Now, in some sense, I'm back to square zero, because the relation that I'm proving itself as a circuit. So I'm proving, let's say I want to prove that a commitment C is a commitment of 13. It's an equality. I want to prove that if I had opened the commitment, the input of the commitment was 13. Now, if I want to do that, it doesn't matter if I have a black box zero knowledge available. My statement tells what I'm proving is that there exists a randomness, such that the circuit of the commitment will give me, with input 13, will give me C1. And the circuit of the commitment can be arbitrarily complex. And this, instead, compare this with the circuit of equality. If I didn't have to deal with the commitment, but I just have to deal with equality, then my circuit will be much simpler. So if I have to prove that I know a secret value V1, which is 13, the circuit is just, do the XOR, and then do the OR of the output, and output not B. So that's all the circuit of equality. And I don't know if you can, probably you can do it even better, but that's the first thing that came up in my mind. So it's just to say, it's just there's a big gap, right, from what you have to prove to prove I know the opening of a commitment. While if you just say I know a secret value which is 13, that will be much easier. Okay, in any case, so how do we leverage black box zero knowledge proofs, and how can we prove commitment in a black box way without using the commitment? This was done in few works for different purposes, not for efficiency reasons. And the idea is, again, I'm going to present it as an information theoretic part and a crypto part. So the idea is that when you commit, let's work in this ideal world where there is maybe a trusted party where we can give stuff. So the idea is that the prover will take the secret value, share it, maybe give it to this ideal party, and then when the prover needs to prove things about the secret, what the prover will do is to act on the shares and do some MPC in the head of the shares. And that's That's how you do the proof in this ideal world. And then you can just add, and the verification, you can prove that the verifier just need to check a few positions of the MPC in the head and a few positions of the shares to be convinced that, yes, indeed, those shares are shares of a certain value. Then you do the compiler, you just add commitments, and then the actual proof becomes commitments. Your commitment is a commitment of shares, and your proof is commitment of MPC views, and the consistency check is unchanged. Right, so that's how, and that's how you do use a commitment in a black box way, and you use only the circuit. Well, here in this MPC in the head, you want to use also the reconstruction of the sharing scheme, but you can be clever and avoid all the reconstruction. We can discuss about it later. Okay, so yeah, so then in the verification, the verifier will ask the prover to open a couple of positions, and we'll do the consistency check. This is how you do commit and prove with one commitment in a black box way. The point here, it's crucial that the verifier at some point needs to see some openings, and it's crucial that the verifier is able to open the commitments. That's the key point. In some sense, it's a cut and choose approach, so I have to open some of the objects that I created. Okay, so this is all you need to know for how to do black box commit and proof. Now, the question is, let's say I want to move to the anonymous setting. Can I use the techniques that we already know? Okay, so let's say, so I'm in the anonymous setting. What is the only difference? The difference is that now I have many commitments, in this case 3. So there are 3 people in the world, and I want to prove that I know one of the openings, and one of the openings is 13. It's equal to 13. So how do I use the black box approach that I've described so far? Well, what I know is my sharing. So I know a sharing that gives you 13. So I do have a witness. And somehow I have to run an MPC in the head. In this MPC in the head, the relation is my parties have 3 secrets sharing, 3 secrets, and one of the secrets is 13. I don't promise anything about the others. And you can always run this MPC in the head. You can just, as long as you have this, you have a right set of shares. The other ones, you just make them up because they can be flawed. That's OK. So potentially, you could do this. You can just run your MPC and send it to the verifier. The problem comes when the verifier asks you to, for the consistency check, the verifier will ask you to open one of the MPC views. And then it will also ask you, OK, let me check if these shares that you use in the MPC proof are actually corresponding to the commitments. And now you are in trouble because you know how to open your commitments, of course. But you don't know how to open other people's commitments. In particular, you don't know how to open these commitments to the value that you use for your MPC. You should not know. I mean, if you know how to do this, then you are breaking binding. So that's where kind of the techniques that are black box, that's where they fail in the anonymous setting, is because they are really relying on the fact that you can open things. It's a cut and choose approach. You want to open whatever object you have to open some parts of this crypto object. And if you're in an anonymous setting, you cannot open other people's object. Okay, so this is kind of where the difficulty lies when you move in the anonymous setting. And the point is, again, you cannot open commitments of other people, and so it will be easily distinguishable what is the commitment that you know and what are the shares that you don't know.
Isn't it also the case in zero knowledge, right? I mean, you're proving is that either like statement A or statement B holds, then you only have a witness for one of these statements, and zero knowledge proof tells you that you can do it without opening the other one. So I don't understand what's the difference between, like, if you can do zero knowledge in the black box setting, then why can't you also do this in the anonymous setting?
Yeah, so in the zero knowledge protocol that I showed you before, in the black box setting, the way I could convince you is by me opening some part of the commitments. That's the way so they have to get around the need, they don't want to use the code, right? So they come up with a new approach where I'm not using the code of the commitment, but I need to open some parts of the commitment. And they promise you that if you open few parts, zero knowledge is still preserved. But you have to open some parts of the commitments. So that trick works if you know the commitments.
Okay, so what you showed before is only zero knowledge for commit and prove? Or
From one commitment.
For general statement?
For commit and prove.
Oh, okay.
So I commit, and then I prove something about the opening of that commitment. Yeah, so it's exactly, it's only for that, it works only for that setting. Also, if you have n commitments and they're not yours, then you are stuck already. You don't know how to move on. Any other question on this? So that's where we are stuck. That technique works if it's your own commitment, you want to prove something about it. Dealing with others, it's a problem. And if you think about it, in any cut and choose techniques, that's the case. We usually use cut and choose for example, if you think of Yao, right? You make your own garble circuits and you open half of them, but you made them. So any cut and choose techniques make sense every time you are proving things about objects you made. But as soon as you move to the anonymous setting, where you have to use objects that you did not make, why you have to use this object? Because you want to be anonymous. Now all the cut and choose techniques will obviously fail because you cannot open other people's objects. So that's the.
Is it easy to make? Is it easy to make Sigma protocols for this thing? Because it seems like maybe it's related to Silka's question. If you can do a Sigma protocol, then you can do this technique where you split the challenge arbitrarily. I mean, and then apply Fiat Shamir. I don't know if this.
Yes, so you're saying that we know the OR of Sigma protocol, where if you know one of these instances, yeah. So if you can phrase it in a black box way, then, but I don't know how to phrase it because I need to say that I know one of the commitments. So it seems that the protocol, that the language itself has the commitment inside. But yes, if we could be able to do this in a black box way, then that might be a way. So that's kind of the challenge where we are stuck. But ideally, we would like, so what we want, we would like to get around this problem, and we would like to, because this approach kind of, it can lead to efficient proofs when, as I said, let's say you want to prove equality, it would be great if I don't have to deal with the code of the commitment. Okay, so how do you get around this problem? You come up with a new commitment primitive, which makes sense for this setting, which we called partially openable commitment. This is a commitment scheme that anyone can open partially. So I can see a commitment of other people, and I can open it, not completely, open it, some parts of the commitment in a way that is indistinguishable from what a real commitment will look like. But of course, I should not be able to give a full opening. So bindings should still hold. And we'll see, if you have this primitive, then you can actually reuse the previous approach almost directly without any problem. So let's look at this new primitive again, how it looks like. It's just like a commitment scheme. The only thing is that it has two additional algorithms, partial open and partial verify. The way we framed it is with this information theoretic crypto approach, because we really want to use it with the black box zero knowledge proofs. So to commit to a message, there is an information theoretic part where you take your message and you split it somehow using some IT, information theoretic system method, and you have your message now is split in n parts, where n is the statistical security parameter. There's nothing to do with the security, the computational security parameter. So, and then you have the crypto part. The crypto part, it's important that the crypto part acts on each part, each sub part of the information theoretic part. So you do crypto, you do crypto on each piece. At least that's how the definition. When you don't care about succinctness, this definition is good enough. This is probably not good enough when you care about succinctness. So the output of commitment then is just these three objects, which are, you can think of it as three sub-commitments. To open, to verify an opening, so you get the commitments, you get all the randomness you used, and the randomness you used for the crypto part, and WI is the information theoretic part. And then you do two checks. First, you check the information theoretic part, and then you do the crypto part. For each I, you check that the verification of the crypto part works out. So that CI is coming from some cryptographic primitive applied to RI and WI. Now, partial opening, this is the new thing that that one needs. Partial opening is a function that takes in input only the commitments. You don't need any secret, any randomness. So you take in input commitments, and you are supposed to output the randomness for each crypto part. You should be able to provide randomness, explain each crypto part independently. So independently, everybody should be able to explain the crypto part. Of course, if I see the entire explanation, it should not make any sense. But if I only look at one part at a time, it should make totally sense. In fact, in partial verify, you have the crypto part and you have partial explanations. And you accept if for that partial explanation, things make sense. So locally, if I look at the J position and I do the crypto part, it actually, it works out.
So it should be all J's in the last.
Not for all J, in the last, it's for some.
It says W star I and CI, that also should be J.
Yes, thanks, should be J. Good, so that's the primitive you want to have. I'll show you how to construct it in a second, but let's say you have this primitive. I claim that now it's straightforward to just reuse the black box approach we have in literature. And why? Oh, then you, of course, from security, you want that the real opening and the fake opening should be distinguishable. And you also want to make sure that nobody should be able to actually do a full opening unless you actually get it. Okay, so I have 5 minutes. So if you have partially open a commitment, you can just plug it into a commit and prove, and then you get anonymous commit and prove. And the reason is that now you can open this part using your partial opening. And how do you implement it? Well, let me just go. So the information theoretic part is a sharing scheme which depends on the MPC you're going to use. So for now, I have not instantiated yet. It can be Shamir secret sharing. It can be a 2 out of 3 decomposition that is used in CKBoo. The important thing is that the reconstruction should be robust. For example, Shamir is not robust because you can have 2 different, if the dealer is dishonest, then you can have different openings according to the sets you use. So you have to change a little bit if you want to use Shamir. Now the crypto part, if you use random oracle, it's very easy. So each block is just a one-time pad. With what? With the output of the random oracle on some random string. So each object, you can always equivocate each object independently. It's very easy. The difficult part is if you were to equivocate all of them, it's very difficult that you were able to equivocate in such a way that you actually hit a sharing of something meaningful. But independently, it's very easy to equivocate. So that's kind of how you do partial open. You do partial open, you just pick a random R, and that's it, and you're done. And that's you decrypt one of the ciphertexts. Now, for the case of equality, now the idea is now if you use the 3 out of 3 XOR for your sharing, and you repeat k times, and then if you use the MPC in the head, which is in ZKBoo, then that's the circuit of equality, that's all you have to implement. For all I, you do this computation, and you output the OR of all the bits, of the negation of all the bits, and I think the negation of all the bits. Okay, so, right, and then I'm going to conclude. So this was the one-time ring signature. So the idea is you can construct ring signature by just using an OR commitment. And I'll skip over this, and I want to just go over the conclusion. So the conclusion is we looked at the anonymous setting for black box techniques, and we basically saw that for commit and prove, you can just achieve the same thing that you achieve in the non-anonymous setting, a black box access to random oracle. Ideally, we want to get rid of random oracle, just have one-way function. I'm not sure if that's possible. And I think the nice thing is that decoupling the crypto part from the information theoretic part can lead to more efficient proofs, also in the anonymous settings. And I think commit and prove has not really been explored from a concrete efficiency point of view. Only the MPC in the head approach has been explored from an efficiency point of view. So maybe it's worth it to look at how can we also get rid of the use of the circuit in the relation. And what's the problem with black box construction is that when you prove once, when you use your secret once, you cannot use it again, because every time you use your secret, you open something. So that's kind of, it seems a major problem, right? You cannot do many proofs using your secret, and so it seems a big bottleneck. So one can for sure can prove, not for sure, I'm assuming you can prove a lower bound that you cannot really do reusable black box constructions. But maybe there is hope to do succinctness, to achieve succinctness. So right now, whatever we show, it's not succinct in the sense that it grows with the size of the group. So if you have n people you want to hide in, then your signature grows with n. So it would be nice to see if you can do something more succinct. And with this, I would like to conclude. So if you have some time for questions, I think I'm done with time. Thank you.
Questions?
In your scheme, if I'm player 2, I make a signature. Can player 1 and 3 convince the world that I did this second signature? Because
Sorry, say it again. If in my scheme?
I make a signature as I'm player 2. Can player 1 and 3 convince the rest of the world that I did that signature? They couldn't.
I see. So you're talking about claimability, this repudiability property.
The opposite is of traceless.
So if people can come together and show that it must have been me, I think they can only prove that it was not them. Of course, if they all come together, they prove that it was not them, it must be you. But they can only prove that it wasn't me. So they can prove it wasn't me.
Normal ring signatures have that. So it's a different notion than computation.
So for ring signature, this is an additional property. So repudiability is not a property of ring. I mean, it has been introduced in crypto this year. So are you talking about repudiability or traceability? So traceability means that if you sign twice,
Yeah. No, but if I sign once, I want to be safe even if everybody else commits. I thought that's what ring signatures achieve.
yes, no, we achieved that.
But you said, but if the other ones can prove that it was not them, then if everybody is ruled out, then it's me.
I don't think you can prove. Can you prove? I mean, can you prove it's not them?
You can prove that it's not you, yes. But the anonymity is defined as long as there is at least one more honest person. That's the anonymity game in ring signature. You always have, because the anonymity game is a distinguishability. I give you 2 indexes, you give me the proof. If they're both honest, I cannot distinguish. But if everybody is malicious, there is no guarantee in the ring signature game. You need at least 2 honest people. In the standard game, you need 2 honest people at least. If it's only you, then there is no guarantee.
Honest in the key generation or honest in the signing part? What do you mean by honest?
Honest meaning not corrupt, but the adversary does not know the secret key. So in the anonymity game of ring signatures, the game works that at some point, the adversary has oracle access to all kind of things. At some point, the adversary gives you 2 indices and wants you to give a signature under one of those public keys. But these public keys should not be in the control of the adversary. That's the ring signature game. So, and I can distinguish, if everybody is corrupt, then there is no anonymity. But this should be, like, if everybody is corrupt, then I know, we all know, like, let's say we are all corrupt, except Puya, we all know that we did not sign, it must have been him, right?
But not necessarily, right? If it's an all proof, sorry. I mean, if you do an all proof with Sigma protocols, like, if I see it afterward, like, if I corrupt the people afterwards.
No, I'm not talking about the construction, I'm talking about the definition. Then you might have constructions that have this additional property, but in terms of definition, the definition is defined as long as there are at least 2 honest parties.
So, one distinction is, can you prove it to another honest party, to a judge, that you didn't sign?
So can you prove that you did not sign?
Yeah.
So I don't have this formal proofs. Can I prove that I did not sign? Yes. You can say it wasn't you.
So then it's a weakness in the anonymity definition, right? Even if
Say it again?
is honest, and we are all corrupt, the outsider shouldn't be able to, we shouldn't be able to convince the outsider that it was who had the sign.
So as I said,
It's a part of the definition of
these are new properties that have been added to ring signatures, but the original definition anonymity holds as long as 2 people are honest. And whether you can repudiate, you can say it wasn't me or not, it can be an additional feature. So it can be, I mean, in some cases you don't want it, in some cases you want it, but it's not part of the original definition.
There's an upcoming crypto paper with all of these.
Yeah, exactly. So at Crypto, there is a paper by Sanu and Alan, I think, where they provide all kind of flavors, what you might want to know, you might want to have no repudiability and stuff like that. Okay, thank you.